Welcome, everyone. I'm happy you could join us for today's sustainability seminar. There are announcements for the other seminars that we have upcoming over on the table here. We have one on November 7th, the 10th, and the 15th. So we'll hope to see you back here for those seminars. There's also a sign-up sheet on the table. If you could sign in, I'd appreciate it. We try to keep track of the number of attendees for these talks. So thank you. We're very pleased today to have as our speaker Dr. Edward Frank. Dr. Frank holds the position of Advanced Biofuels Scientist at Argonne National Laboratory, where he uses life cycle analysis techniques implemented with the GREET model to study emissions and sustainability of transportation fuels and transportation systems. His work currently focuses on algal biofuels. GREET was developed at Argonne by Dr. Michael Wang and has been applied to many transportation, fuel, and vehicle systems. Relevant other work includes collaboration with the Process Technology Research Section led by Dr. Seth Snyder, and both groups are in the Energy Systems Division. Dr. Frank's presentation today will be on life cycle analysis of algal biofuels. Thank you, Dr.
Thank you. It's a pleasure to be here, and thank you for inviting me. I'm going to talk about the work that several of us have been working on. Michael Wang is the section leader in our group and has been doing life cycle analysis for quite some time at Argonne and developed the program there. I've been focusing on the algal work that I'll present today. Zhang Wu and Amgad are both mechanical engineers, and as their background and bring in those skills. Then Ignacy is a chemical engineer with experience in the petroleum refining industry. I'm the odd man out because my background's actually physics, so this was a new area for me to be working in. I'm going to be summarizing a report that we put out a couple of weeks ago. So if you're interested in more details, you can download it from that address, or you could just go to Google and just Google for GREET publications, and that'll get you to the right area, and you can locate it there. So let me start with motivation and background and approach. So there are various kinds of algae, macroalgae, seaweed, and microalgae, which are typically unicellular. You can find them in fresh water or salt water. There are many different kinds. Microalgae are nice in terms of growing biomass because their metabolism is focused on growth. There's no woody structure to them, no support structures that they need. And they grow in several different modes. Autotrophic is a growth mode in which they're relying on CO2 and sunlight. Heterotrophic grow in the dark, making use of carbon that's already been reduced from other sources, sugars and so forth. Mixotrophic, sort of an in-between case, autotrophs that can, or heterotrophs that can make use of photosynthesis. So they need few inputs, light, water, nutrients, carbon in some form. And they've been grown at large scale for nutraceuticals in the past. There's a picture here of cyanotech in Hawaii. And the question is whether or not we can carry that over for producing biomass, with the idea being it would complement other sources, other kinds of crops, and it has the advantage of potentially having large productivities, large amounts per unit of area. The fact that it's been grown before for nutraceuticals is somewhat encouraging. On the other hand, the value of nutraceuticals is so high compared to an energy crop that really you need new methods of cultivation. If you're producing something that's just has such a small margin compared to, say, astaxanthin or one of the other nutrients, you have a much larger economic and technical challenge. So again, continuing with this sort of quick overview of what the algae process is, I'm going to focus on the use of microalgae, not macroalgae. And so we're looking at a process in which we're growing planktonic microalgae. So you're looking at dilute suspensions, maybe half a dry gram per liter at harvest. The process continues by first dewatering and then extracting lipids after cell disruption. The lipids can be a few percent to 60% depending upon the species. You need to be at the higher range, let's say 30, 40% it seems to be, in order to start having some chance at having economic success. You then convert the lipids to a fuel, perhaps by transesterification or by feeding through a refinery through some hydrotreating process. And the challenge here is that the total energy content of the algae is only 18 kilojoules. So you have to achieve all of this with a very small energy budget, right? If the algae were 30% lipids, that would be about 6 kilojoules in the product, and leaving you a balance of about 12 kilojoules to achieve all the other steps, including a large amount of water movement and dewatering. So there are two basic approaches that people are looking at. Let me start on the right-hand side here with the so-called raceway ponds or open ponds, in which one tends to put as little infrastructure as possible into the growth approach. So here there's been some excavation and plastic to protect against erosion from water when it circulates later. In some cases, depending upon the soil chemistry, the soil conditions, if there's enough clay, you'll just compact the soil in the bottom. In other cases, you would have to put in a plastic liner of some kind. You then maintain the suspension with a paddle wheel in this approach. Now, the second approach is to make use of photobioreactors. These are much more complicated. So rather than moving some dirt and putting some plastic down, you have steel racks, you have plastic tubes, you have a greenhouse in this case. This one's a little simpler with plastic bags in which you're growing the algae, but it's much higher, much more infrastructure here than in this case. So there have been some techno-economic analysis done in the past. Benneman and Oswald, for example, did a study in '96, and they concluded that even for the open pond case, you can't even afford to put the plastic liner in. You have to have the clay soil, or else it destroys the economics of the process. So you have two approaches, really. In one approach, the open pond approach, your strategy is keep costs as low as you can. In the PBR case, the strategy is we're going to make up for our extra cost by increasing productivity and by improving the reliability of the culture because it's a closed system. I'm going to focus on open ponds in this analysis, partly because of the economic reason, partly because it's easier to find a consistent set of data describing the process for the open pond. So I'll be focusing on open ponds in this. So who are the players right now in doing algae? Who's who? But the question may be who's not. Everybody's getting involved in this. And the list of people involved range from some sort of the Levi Strauss companies whose business model is to sell equipment to the other businesses, most of whom will go out of business, and other companies, like let's say Sapphire, who are doing the entire process end to end. So you find all sorts of people involved, and you also find government involvement, projects funded by DOE. NAABB is probably the largest one amongst the current DOE consortia, and then there are several others that are looking at a few particular focused issues like suitability, feedstocks, and so forth. And then there are a few integrated biorefinery projects with a few companies that have been sponsored to look at scaling up. So the question is it a sustainable approach? If we made this work, would it be a good thing? And there are many issues to consider. Land requirements, land use change associated with this, water consumption, nutrient requirements, where would you get the CO2, various kinds of emissions, eutrophication potential, and so forth. What I'm going to focus on today is talking about airborne emissions. In particular, I'm going to focus on greenhouse gas emissions, so emission of methane, nitrous oxide, and CO2. And the question is, do algal fuels lead to more or less emissions compared to the fuels that they replace? That's what we want to answer. Ultimately, one of the things driving the process is the Renewable Fuel Standard, which defines an advanced biofuel in terms of its reduction in greenhouse gas emission relative to the fuel being replaced. To qualify, in this case, you would need to have a 50% reduction. So there are various sources of emissions that you can consider. You can consider the direct emissions that occur during your process itself if you burn, let's say, natural gas in a boiler. There are also emissions upstream, so energy used that you use to obtain feedstocks or to produce chemicals. In this case, let's say nutrients such as ammonia, urea, triple superphosphate. Energy used to transport materials. And then there are downstream emissions. For example, when I burn the fuel in an engine, and there are many different fuels that you might produce, different efficiencies for using them. Life cycle analysis is one approach to answering this question of have we produced something sustainable, at least with regard to GHG emissions. And the approach then is to consider all these various emissions I just described within some systems boundary that maintains a fair basis of comparison between the two scenarios that you want to compare. So your trick is to make sure you make this big enough that when you compare one versus the other, you aren't accidentally excluding some change that really affects the two. But not to make it so large that you dilute your results or increase the amount of things to consider to the point that you just start introducing additional irrelevant uncertainties. So life cycle analysis then is sometimes called cradle to grave, but maybe that's a little misleading. That's what it will be in this case, because for this particular problem, we need a very broad system boundary. But you just need the boundary to be sufficient to allow a fair comparison. But as I mentioned, it's a matter of choice. A second issue to consider in the analysis is when you look at the emission burdens encountered in the process, we're thinking in terms of producing a biofuel, but the processes produce multiple products. And so you face sort of the accounting problem of how to distribute the charges, the burdens, and the credits amongst the various products being made. And there are different ways to do it. And according to the way you choose, you'll get a different answer. And it's not necessarily right versus wrong. It's more of an issue of systematic uncertainty in the approach. Now, life cycle analysis has been integral to DOE's approach to developing new technologies and new fuels. And I'll mention another slide how that ties in. But in this project, what we wanted to do is we wanted to achieve these three things. We wanted to identify key issues affecting algae life cycle analysis. It's very early in the development stage for algae, so we want to understand what the key variables are. We want to compare the important process options. So in other words, exercise those key issues that we find and see how much the changes are. And we wanted to facilitate community life cycle analyses. And what I'm referring to here is these systematic uncertainties I'm talking about with regard to system boundary and allocation methods. Makes it very challenging to compare what's in the literature right now. As people look at the different options for doing algae, you see a difference, but you don't know if it's actually fundamental to the process or it's just because of a difference in the way that they approached their analysis. And we want to find a way to facilitate making those comparisons. So let me give a quick overview of the LCA work that's been done so far. There's been an explosion in the literature, so this is probably only a half to a third of it. But I wanted to highlight sort of the key ideas that have come up to set the context for the choices that we've made in our analysis. So CADM looked at a coal power plant that was co-fired with algae. And the algae was grown on CO2 from that coal power plant's emissions. And one of the conclusions that that study reached was that GHG reductions were possible, but if you did CO2 capture with monoethanol amine at the power plant, the steam required for regeneration then disturbs the energy balance sufficiently that you reduce greatly the benefits that you have. So that study led to the direction of let's just look at flue gas if that's going to be your CO2 source, and let's put aside looking at CO2 capture. Campbell, though, then looked in the potential for doing this in Australia, and they found that 7 of the 9 power plants that were good candidates for constructing this didn't have sufficient land nearby to absorb the CO2 being produced. So they had to consider transport of the CO2, the flue gas, over further distances, and discovered that if you pressurize the flue gas, you use 30% of the energy in the algae. And this goes back to that energy budget at the beginning. So this leads us to the point of saying, well, we're going to look at low pressure transfer. Lardon considered open ponds and doing hexane extraction, but didn't really go into detail in treating the residues that were left over. So you pull the lipids out, you still have a bunch of mass left. And he didn't go into detail of what happened there, but concluded that you have to avoid drying. If you simply dry, it takes too much of the energy to get dry enough before you go into a sort of dry process that you would use similar to soy. They also concluded that although they didn't go into detail of how they're going to treat it, much of the energy in the biomass remains in those extracted lipids. So again, if you had about 30% lipids, about half of the energy still remains in the rest of the biomass. Clarence only looked at the biomass production site, not the processing of it, but compared versus corn, switchgrass, and canola, and pointed out that nutrient demand, if you didn't have recycling of nutrients, could cause the algal biomass to have higher emissions than other energy crops. So it's going to be important to think about nutrient return. Stevenson looked at raceway versus airlift tubular photobioreactors and pointed out the importance of considering the mixing energy just to maintain the culture, and found that the PBRs were 8-fold higher. Now, Stevenson's study was at 30 centimeters per second for mixing, and that's actually pretty high. If you look at some older studies, you don't need to be that high. It depends on the species that you look at, but the key thing is that the power consumption goes like the cube of the velocity. So that's a very sensitive parameter. Collett and Rast looked at algal biomethane itself as a transportation fuel, so not a liquid fuel, just biomethane. They went into some detail with regard to the anaerobic digestion of algae, and we're going to carry some of that into this study. And Moeller looked in the context not of transportation or algae, but in terms of, or rather not in terms of algae, but was considering various emissions related to biogas production and identified fugitive emissions and N2O emissions associated with AD. And we'll talk more about that later. Our work's going to try to carry those into the context of making liquid fuels from algae. So let me talk about GREET. Personally, I can never remember what GREET stands for. Right? It stands for Greenhouse Gases, Regulated Emissions, and Energy Use and Transportation. It's a life cycle analysis model developed and supported by DOE since about 1995. It's freely available. Our intention, Michael's vision has always been to keep the data provenance clear and allow you to see all the data that's present so that we can get feedback on it and people can understand what goes into the analysis. We have a new version that was just released a few weeks ago, and that new version has been expanded to include algae. There are about 15,000 different users for GREET. You'll find there are two basic chains in GREET. One we refer to as the fuel cycle. And in this portion, the system boundary includes all the activities related for fuel production, combustion, and use. And the second is the vehicle cycle, which relates to the materials involved in utilizing in constructing a car and then recycling and return. So this is an example system boundary. Our system boundary for today is purely in the fuel cycle. So with regard to life cycle analysis, GREET focuses on gaseous emissions and energy consumption. So the energy use is both fossil and renewable energy is considered. For fossil, you can see how it breaks down in terms of petroleum, natural gas, and coal. It considers renewable energy, that is energy in the biomass, as well as other renewable energy sources. And for greenhouse gases, tallies production of CO2, methane, and nitrous oxide, and then combines them by their global warming potentials to get an overall CO2 equivalent. Various criteria pollutants are also tallied. This isn't going to be so important for the algae at this point. Although we're computing them, we haven't gone through the detailed process yet, as we have with the GHGs. So GREET considers many different feedstocks for producing fuels, various fossil fuels, various kinds of renewable fuels, and looks at the production of many different kinds of fuels. And so all of these have been available for doing life cycle analysis. And this context would allow us, if we add algae, like we have down here, to then be able to compare the results with many other transportation fuels produced from many feedstocks and compare them on a much more uniform basis systematically. So that's our thinking in going into this project. And so our approach has been the following. I mentioned the challenges for algae life cycle analysis. The commercial pathways that I sketched before, they're not very well defined. It's very early right now. There are many scenarios to consider. And that partly means or implies that you need many analysts looking at this in order to cover the analysis space. But it's difficult to compare them right now. And there's a lack of validated data. Much of it's proprietary, held close to your chest. And as I mentioned, the published LCAs differ methodologically. So it's different. It's hard to compare them. So by working within the context of GREET, we hope to address several of those. Now, we produced an additional helper tool called APD, or Algae Process Description. It's not a process model, but it's an inventory of various unit operations with a few parameters for each one that allow you to rapidly assemble a pathway for analysis. So we're looking for this as a means to facilitate collecting process information from people and then make it easier for them to swap out one piece for another to see the effect of putting in their particular piece or changing particular aspects of the model. So in APD, what we've done is we've abstracted the process to be several steps. The first is growth and first-level dewatering, followed by the secondary dewatering. These two are grouped together because almost all of the water movement occurs within those two. By the time you get down to the sort of secondary dewatering, you've accomplished about 95% or more of your water movement. So we've gathered these two together. This is followed by extraction and then conversion of metabolites to your fuel. Transport refers to transport of intermediates, not using the fuel. That's different. And then various recovery processes for recovering energy from the residues or recovering nutrients. An example of what APD looks like, sorry for the typo, there are a number of drop-downs that you can use to select the various unit operations you want to put into your process. So in this case, I'm just showing the configuration box for doing the secondary dewatering, and we've chose to use dissolved air flotation followed by a centrifuge. And for each process, you list any materials that are consumed. Each of these things that says none are drop-downs that you can use for putting other materials in. In this case, there's a coagulant, chitosan. And then you use your list process fuels that are directly consumed in your process. You explain the relationships between input to the output being produced by that stage. So here we're talking about how much dewatered algae is produced for each unit of input algae. If there's produced CO2, how much is being produced so we can recover it in the process. And then how much mass might flow to recovery. So if you had additional processes that you wanted to contribute, this would be the format of what you would be contributing. We don't need to open any boxes, and I hope that helps get around some worries that people might have with regard to IP and help make it easier for people to share some of their data. Back on the GREET side, that's where you configure the life cycle analysis proper. So one of the key issues there is handling of co-products, and we handle several so far. One is to take the lipid-extracted algae through anaerobic digestion to produce biogas, from which, by combustion, you can produce electricity and heat that might be exported as a co-product or reused in the process. You might do further cleanup to produce biomethane that could be exported. You might consider residues that could be used as soil treatment, or you might consider its use as feed. The analysis I'm going to be presenting today focuses on this path across here, producing electricity and heat for reuse in the process or export of electricity as a co-product. Okay, so now let's talk a little bit about what's being included in the system boundary within our analysis. So we're including everything upstream for our production of input materials, in particular fertilizer and CO2 supply, through its combustion and fuels, and then the production of the algal residue after digestion and its transport for use in soil, and emissions of N2O from the soil. So the processes, as you move across, are the algae and lipid production, which has various co-products like electricity. I just mentioned the soil amendment. There's then transport of lipid to where fuel production happens, either biodiesel, renewable gasoline, where there can be co-products like glycerin, heavy oils, and fuel gas. And then that's transportation to station for use. So there's a supply of energy and materials to each of these steps, emissions from all of them to air, which then have to be accounted for. So we're focusing on open ponds, and we're excluding infrastructure materials, for example, any cement that would be used in construction of the facility or plastic being used. And we're not considering land use change at the present. Our reference pathway is low sulfur diesel, and I just want to make the point that the scope of the pathway is comparable. We're looking at all processes upstream from procurement of all the essential materials needed to produce the fuel through its eventual combustion. So the comparison between the two is, to the best of our ability, apples to apples in terms of scope. So the flow of carbon through the system is fairly involved. We start with carbon in the fuel going into the power plant. We're looking at the case where we're feeding the algae with CO2 from flue gas from a power plant. So C in carbon and fuel in coal or natural gas ends up as C in flue gas, which is used for growing algae, which then flows downstream to produce fuel, which is eventually burned, goes to the atmosphere. You can lose carbon through CO2 that isn't captured by the algae. You can have C from various emissions as you move along, for example, from if you're running a boiler. The other emission that I want to point out at this point is when you look at the biogas recovery, part of the carbon that started off here can end up as fugitive methane. And these guys have different global warming potential than CO2. So you need to account for that difference. And I want to explain how we handle that. What we do is we do a kind of, we refer to as back-end accounting. What we're going to do is, let me back up one step. There's an important point to make. In the process here, although all the C in the fuel originated from fossil fuel, the sort of philosophy behind the analysis, and this is common amongst all the algal analyses, is that with or without the production of fuel, the power plant is going to operate. So the CO2 would have been emitted anyways. And for that reason, the CO2 is being treated, in a sense, as biogenic. It's not being given a carbon debit, in a sense. Right? Because were we not to make this the algal fuel, it'd end up in the atmosphere anyways. And so taking it from the power plant, in a sense, is being opportunistic and grabbing atmospheric CO2 before it's been dispersed and become too dilute for us to actually use. So in the accounting, what we do is all the carbon that traces back to the power plant is treated as if it was biogenic, and all others are anthropogenic. So what we'll do is we'll look at all of the emissions from our processes that occur, and we'll incur a penalty for them. So if I have during biogas combustion any sort of CH4 emission, it will be accounted for according to its global warming potential. And then in the end, we're going to take a credit according to the flue gas CO2 that we had upstream. And in that way, we can account for the fact that there's been this change in global warming potential for some of the carbon involved in the process. In our process, we grow algae, produce oil. The remnants go to an anaerobic digester, which is used to produce electricity and heat, which can then be used to meet some of the demand that's used for the process, required for the process. In our analysis, what we do is this reduces our imported electricity and natural gas demand. So our approach is to only count our energy consumption here. Rather than some analyses, you'll see what they do is they consume all of this according to their demand and then subtract a credit for the emissions for the equivalent that they displaced from their own analysis. So rather than taking this as a displacement on the emission side, we just look at our net consumption on site. We feel it reduces the uncertainties in the analysis by doing it that way. All right, so these are the on-site processes. The algal oil then goes on to a conversion process. And I mentioned earlier we have to address this accounting problem of how do we allocate or distribute the charges for the emissions amongst the various products being made. And we use a hybrid approach. So what we do is I call this algae, maybe I should have called it lipid because this goes all the way through the lipid delivery to the conversion step. We look at the various things that can be made: oil, co-produced power, co-produced methane. And also in this step, we have this residue that is displacing agricultural fertilizer. So what we do is we take the total emissions for the production of the lipids and we take a displacement credit for the fertilizer, because its natural basis for assessment is the greenhouse gas emissions in its production. Treating it on an energy basis or treating it on a mass basis isn't really the germane variable for that particular thing. We then allocate those emissions to the lipid portion by an energy allocation method. So in our case, we aren't producing methane. It's just the distribution between the oil, the lipids being produced, and co-power. These emissions then are fed into, or these steps are fed into the biodiesel production step. And there again, we make an allocation to the biodiesel according to an energy allocation between the biodiesel and glycerin. So the emissions at that step are then allocated, and then this is treated as an input that again is allocated by that same fraction. Now, why do we treat glycerin on an energy basis? Again, you might treat that on a displacement basis because it's a chemical, right? Our expectation, though, is that at the scale that you would be looking at for producing transportation fuels, the market for glycerin will be more than saturated. And so more than likely it will end up being used as a process fuel on site or for some other purpose where an energy basis would be a better treatment. So these aren't the only ways to go about it, but it's the way that we went about it in doing the allocation in our particular analysis. Okay, so that's the introduction, the motivation. So let me describe in more detail the pathway that we're looking at. Let me back up here quickly. What we're going to look at is in this broad picture, I'm going to expand this one box. So we're going to look at growth in an open pond. The first level dewatering is done by bioflocculation. And this is a process by which the algae have a negative surface charge and would prefer to just stay in suspension. But there is some belief that one might be able to adjust growth conditions at an appropriate time to allow them to flock and then settle out. Pretty much any other approach is suspected to be uneconomical. So although this process isn't demonstrated, it's commonly assumed. So it's one of the weak points in these sorts of analyses. So we use this as our first level of dewatering, followed by dissolved air flotation, a common process for wastewater treatment, followed by a centrifuge. So what we're doing is we're looking at processes that increasingly use more energy for their process, but are handling less and less water. We go 0.5 gram per liter to 10 grams per liter, and then to 200, and that's actually in 2 steps. In theory, there is a transport step to take the biomass over to where you're going to do extraction. In our case, we're considering a wet process, so transportation wouldn't be feasible. So we don't include a transportation step. Instead, it goes to a pressure homogenizer and then a wet hexane extraction process. The residues then go to a digester to make biogas. The biogas is combusted to make electricity. The CO2 is recovered to the pond. Electricity can be brought back to the process or exported. And the nitrogen and phosphorus from the digester, the liquid portions return to the pond. The solids are then transported for use as a soil amendment. And I'll be the first to say that these steps are not demonstrated. Well, maybe that one. These steps is not demonstrated that the algae will actually grow successfully in that context. Okay, so the energy numbers, the data provenance for what we're using, there are several sources of estimates for the mixing power with paddle wheel. It depends on the mixing velocity. One of the earlier studies was by Weissman. He studied numerous species at different mixing speeds. Different species have different size, and so they need different mixing speeds to maintain the culture in suspension. Benneman used this spread of values to estimate a speed typical for what would be an expected crop. And that number was then, these inputs were part of Lundquist's study in 2000, which went into a little bit more detail and considered the potential for reducing circulation speed at night and was able to save a little bit of energy. But some other bits of realism also brought the number up. So this is the number that we end up using, and in various scenarios where we change the mixing speed, we scale that number by V cubed. For pumping power, you need to move water in various ways during the process. Water has to move from the pond to settling and then move back again. Water evaporates from the pond, and you have to pump in water to make up for the evaporation. So to estimate the pumping cost, we used a simulation package that's used for wastewater treatment based upon some work from Harris in 1982. So these are sort of rules of thumb that are commonly used. And we used the portion for intermediate water, which is water that can be treated like water. In other words, not thick, mucky stuff that needs its special pumps. And in that case, the rule of thumb is 15 feet total head for transfer on site, with a rule of thumb for energy consumption. And we treated this as good practice and used that for our energy estimates. There's a good chance that this might be an overestimate because a waste treatment plant is a more compact facility than a large distributed algal structure. So there may be sort of a cost optimization. You may find that there's some optimization there, but we treated this as good practice and used this for our energy estimate for pumping. Anaerobic digestion. We surveyed the literature to see what was available in terms of data for digestion. And there are a few studies. However, they're pretty much all looking at intact algae, whereas what we would be looking at would be the residue after lipid extraction, and that changes the carbon-nitrogen balance in what you would be digesting, greatly increasing the nitrogen portion. So the only study we found with lipid-extracted algae was this small one. I'm not sure of how the author's name is pronounced. They found an interesting, let me say that differently. One of the results was that for them to get good methane yields, the substrate concentration in their digester was about 10-fold less than what would be typical in a existing production digester. So rather than 5%, it was more like 0.5% what they found they needed in order to have decent digestion. The other studies had a spread of values. If you look at the yield of methane on a volatile solids basis, that was pretty broad. What we did was we expressed this on a total solids basis because that facilitated our computations of mass flow through the system, and everybody was about the same on the ash content. And so this spread of values, the middle of the distribution is about 0.3, and that's what we ended up using to represent our biogas production. So as I mentioned, there's this uniform, fairly constant result of the ash content. We use the center here for our production of methane, and to then calculate the biogas production, we use 67% on methane content in the biogas. We then use Collett's assessment for thermal and electrical energy demand for running the digester. And his consideration was for a completely stirred mesophilic tank. His residence time was quite long, actually, compared to what would be a real problem. Usually this number is more like 20 days. So his energy consumption here is probably higher than what one would need. On the other hand, the digestion that we saw in the other slide is poor. So perhaps maybe that is a good estimate. We look for information concerning direct emissions of methane from the anaerobic digestion process, and we found two studies. One by Flesch. This is a study in Canada of a fairly modern advanced digester. They found 3% total emissions, most of which occurred during loading of biomass into the digester, during periods of maintenance when they had to open the digester, and during flaring to handle overpressures. Now, this value fell to just about 2% when they redesigned the hopper to keep it at negative pressure. Liebetrau looked at 10 different biogas facilities in Germany and found several sources within the plant. These two approaches use completely different methods for measurement. Liebetrau's method was to identify potential sources of leaks within the digester, and then build a hood over that particular part, and then assay the collected gas. And he found several sources, ranging from 0.1 to almost 2%, and noted the important point that the digestate that's taken away from the process still contains substantial potential for further production of methane. And so the method by which you store the digestate, since its application to soil is seasonal, is an important consideration. Right? If you don't put the expense into covering and recovering those, then your methane emissions could be substantially higher. So based on these, we estimated maybe 2% for fugitive emissions. For direct N2O emissions from the digestate when applied as a soil, as a fertilizer, as a soil amendment, we use the IPCC methodology, which is 1% grams N2ON for each gram of applied N. And they consider all N in the sample, not just the bioavailable N. The bioavailability of the nitrogen depends greatly on soil conditions. But to take a sort of typical value, we use Metcalf and Eadie or paper by Bruin to say 40% might be representative. So what happens here is because the bioavailability determines how much fossil or mineral fertilizer you displace, and that's only a fraction of the N, yet all of the N leads to an estimation release of N2O, you end up with a net N2O release relative to the fertilizer that you displace, and we included that in our emissions burden. I would say that this is not cut and dried. There's a lot to discuss here and to understand further. But this seems to be the methodology suggested by IPCC, including a recent review, I think in 2006, based upon a number of publications has happened since their original suggestion. Combined heat and power, we used the performance of a gas turbine at the 30 megawatt scale, which is consistent with the sort of size facility that we would be considering, and use that electrical efficiency and heat recovery to estimate how much electricity would be recovered to the process. Nutrient recovery. Again, this is not a demonstrated capability returning nutrients from the anaerobic digestion to a pond. The basic idea is that the digester mineralizes nitrogen into the supernatant, and that becomes available for use in the pond. But there's a lot more in that supernatant that could affect the algal growth. Weissman and Goebel estimated that something like 25% of the N remained in the sludge and 75% would remain in the liquid, and the phosphorus would be split evenly. The nitrogen would likely suffer 30% outgassing when returned to the pond. Now, Ras had some experimental data looking at chlorella and found about 70% of N was in the supernatant at 28 days digestion. Collett, in their study, extrapolated this to 42 days to get to a higher digestion and thought that maybe 90% would be in the supernatant. And if you could keep the pH low, you'd reduce the volatilization. So based on sort of all this hand-waving, having to choose a number, we estimated maybe 80% N in the supernatant and 5% volatilization in return. And phosphorus 50-50 between the two, with both being used at 100%. Later, I'm going to describe an alternative process than AD for producing biogas. And that alternative process is able to do better than this. So although this data isn't established, I'm going to use those values because this other process sort of sets the bar these guys will have to meet. And so that's another reason for using those. But I think there's a lot of uncertainty here. To compute our nutrients, we just do a rough mass balance. So based on the stoichiometry of CN and P in the algae and its flow down to digester solids that then go out to the soil or to liquids returned, we can figure out how much nutrients we need to consume. For the oil extraction portion, there are some models that people have used of wet and dry processes. Lardon made some based on sort of a volume scaling. Stevenson made a Hysol simulation, and from them estimated the thermal and electrical power. So we use these to take sort of a representative scale value from these for the baseline case. So all put back together, what we're looking at is we're looking at algal growth at 25 grams per square meter per day and 25% lipid, which is a fairly conservative. It's aggressive relative to what people have demonstrated, but conservative compared to what people are promising. We then proceed through the various places that I described already, sort of 90% efficiency for retaining algae during dewatering in each of these steps, 90 and 95, 90% efficiency for homogenization. The lost biomass then flows off to the digester. Okay, so let me move on to results. So it's a lot of information I'm dumping on you. I wanted to give you the context for what went in. Okay, so for energy balance on site, what we find is that based on that model for anaerobic digestion, which I think has lower methane yield than what other studies have used, we find that we're unable to meet the electrical demand on site with what's produced through CHP. And so we need to import additional electricity, this guy here, to meet process needs. On the other hand, the waste heat from the combined heat and power is adequate for all of the thermal needs for the anaerobic digester, as well as the thermal needs for the wet hexane extraction. In fact, we have additional heat that we throw away. So there's room for doing additional thermal processes on site if possible, and that would increase our energy recovery. For CO2, about a quarter of the demand can be met from the CO2 recovered from the CHP. The rest then has to be brought in. Okay, so total energy and petroleum use. In each of these, I'm going to compare the conventional low sulfur diesel with algae biodiesel. Let me start with the petroleum energy use. What you'll see, thought I had another slide in here, which I guess I've left out. I want to remind you that the coloring here, the pump to wheels, this portion, refers to the utilization of the fuel in the car. So you can think of pump to wheels means use. The blue, which is well to pump, basically means production of the fuel. So we have production in blue, use in red. So for the algal case, since we treat the carbon as biogenic, there's zero emissions during the use portion. So we're only comparing the petroleum energy use between the production phase. And for that reason, you see substantially less. If you just look at production, it's very comparable. It's coming mostly from the transportation steps, which are comparable in the two. But we avoid the use of petroleum for the actual fuel. For total energy use, it's substantially higher. But this includes energy in renewables, right? So this includes all of the energy that was in our residue that we burned to produce electricity and suffered the thermodynamic loss of maybe 2/3 for the electrical efficiency. So that's why this number is looking particularly big. This is a combination both of that factor plus the energy demand of the process. In terms of fossil energy use, the process for producing the fuel from algae is roughly twofold higher than the fossil energy consumption for production of the conventional low-sulfur diesel. And we'll break this down in a second to see where that's coming from. But we avoid the fossil energy in the combustion phase, so there's a net savings. For the GHG emissions, there are two components. There's a credit portion, which comes from the production phase, and we'll break that down in a second. And then there is the GHG emissions during combustion, which together combine to produce about 55,000 grams CO2 equivalent. So roughly a factor of 2 compared to the baseline scenario. So there's substantial savings in this baseline case. It depends a great deal upon the accuracy of the energy recovery, as I pointed out, and the reuse of the nitrogen and phosphorus. So let me break down these other two a little bit so you understand where they come from. So this bar right here I'm going to break down, right? The GHG from the production portion. So that's this guy. So that guy comes from two things. One is emissions during the production phase, which then is offset by this biogenic credit that I showed you earlier on, where we take a credit for the CO2 that came from the power plant. The point I want to make is that what looks like a credit here, it is a credit, but it's the difference of two substantially larger numbers. And what that means is that if I had some fractional uncertainty in one that was uncorrelated with the other, the resulting uncertainty will be relatively larger for this net. So there's sort of an uncertainty amplifier here. So you need to keep that in mind. We need to know these two guys fairly well. The second point I wanted to make was when you look at the contributions to the GHGs, this is our net GHG output. So this is that 55,000 grams. And it comes from a portion from the fugitive methane plus the N2O. So those two things that we considered did end up giving substantial contributions to the process. And so they're worth going into more detail to fight our way through the uncertainties in the contributions to them, because they are having an important effect. Now, one of the conclusions from that is because these do give a substantial contribution, it's important to think about the technology choice, operations and maintenance that you're going to use in your process. So if you're doing techno-economic analysis, you have to be careful of shortcuts for CapEx and operating expenses in those particular areas. And we also need to better understand these N2O emissions. So a breakdown of the fossil energy use. If I kind of go around the pie chart here, the CO2 transport and CO2 return are both electrical processes. We're running in our way we've modeled this. This is basically fans or compressors. Nutrients are making use of chemical processes upstream. So this is, for example, natural gas for production of ammonia. Mixing and pumping are both electrical. The second, dewatering is electrical. Oil extraction. Remember, we met all of our heat needs from recovery from the CHP process. So this is really coming from electrical consumption. Anaerobic digester, again, we met the thermal needs. So again, this is electrical. So most of what's here is coming from electrical demand. So what you would look for in producing a process is either the ability to use some of the thermal energy that we're throwing on the floor when we're done with CHP, or look for ways to reduce electrical consumption in the process that you're using. And a lot of the energy is coming from water movement and water handling in this portion here. With regard to the credit that we get from the use of digestates as fertilizer, we see the net credit is the combination of a credit for displaced fertilizer, which then suffers losses from the, I'm pointing to these upside down, I'm sorry, which suffers losses for transport of the material and then for the N2O. And again, we have one of these circumstances where we have two larger things countering each other. Now, one of the things here is this carbon sequestration credit. And what that corresponds to is the fraction of carbon in the digestate that will remain in the soil. We used an assumption of 100 years retention in the soil and used some numbers from Bruun, who estimated 8% retention, although expressed the expectation that really you would expect all of that carbon eventually to end up in the atmosphere. The point being that it depends a great deal on the soil. If it's a very carbon-poor soil, you might find that you can have an opportunity to accumulate carbon and have a much better effect than what we're showing here. On the other hand, if this were reduced by very much, then you might find that this just goes to zero. So it depends a great deal upon the local soil chemistry and the details of what you're doing. We did a sensitivity analysis looking at various parameters since there's so much uncertainty in the process. And I guess what I want to point out is the key variables here are things related to water movement, our ability to produce methane, so in other words, the AD performance, the lipid fraction and the productivity, and the efficiency for producing electricity from CHP. We're up at the top of our list. In a sense, what I want to make a point about this sort of chart. So it's just a moment for me to sort of jump back to my physics. In a sense, this chart is a bit of a cheat, and you need to be careful with them. Because what we've done is we've chosen a range of values and then looked at the change in GHGs. I've said nothing about the probability of those guys changing. Really what you ought to do for a good tornado chart is that each of these parameters should correspond to the same confidence level for each of the parameters. So these guys stack up in size relative to the same expectation value, or the same probability. We don't know the distributions for these values. So when you see these charts for algae, I encourage you just to think of them as, well, maybe if you divide by these, you know the derivative at the center. And then just think carefully about it, because they really aren't a tornado chart, so be careful with them. But it does show you the effects of these various variables. Two of them I want to point out is, if we had done extraction without recovering the heat from CHP, so let's say we had a regional center for doing the extraction rather than doing it on site, you would increase your emissions by a little bit over 10,000, maybe 12,000, relative to the 55, because you'd have to burn fuel in order for the hexane recovery. We considered two other emission scenarios to compare with our baseline, these reduced emission scenarios. In one of them, we increased the lipid fraction to 35%. We did that for both of them, actually. But in this one, we replaced the anaerobic digester with a catalytic process, catalytic hydrothermal gasification, which is a kind of thermochemical digester. Despite its name, it's not like a thermochemical gasification process that's producing syngas. All the reactions occur in water. It's more like hydrothermal liquefaction in its essence, in which you then bring the soup past a catalyst that does reduction of nitrogen and carbon to produce ammonia and methane. And so you end up with high recoveries of nitrogen and phosphorus. The people developing the process actually report almost complete recovery of N and P, but we backed off of that to 95 and 90 just because, to be prudent. The phosphorus, the nitrogen is recovered as ammonia in an essentially sterile aqueous phase that comes off. The phosphorus precipitates out upstream in a sort of clay-like, apatite-like material that you can recover it with sulfuric acid. because this is a very condensed process, small process, more akin to the sorts of processing that you do, for example, in natural gas cleanup, it's quite plausible to think that you'll achieve the sort of fugitive emissions that you see in those sorts of processes. So we reduced the fugitive emissions down to 0.2. Now, to be on the conservative side, we took these benefits, but then we took a couple of hits and a couple of things. We reduced the CHP efficiency to correspond to saying we don't know the utilization factor. Right? We might be working below its rated limit, which reduces their efficiency. And we reduced the DAF performance from 10% output to 8%, which is, in my opinion, a little bit more plausible. The second scenario worked just by increasing the lipid fraction, increasing the productivity, which we didn't change here. Assuming that we were able to get the fugitive emissions down in an anaerobic digestion process. And we took sort of a middle of the road. I showed you that span of values for the energy consumption in the hexane extraction process, and we just took a middle of the road there. But on the other hand, we said, let's say the carbon sequestration doesn't happen. So when you take those two scenarios, the 55,000 drops down to roughly 40,000 or down to 36,000. This was the catalytic hydrothermal gasification, and this was the sort of reduced extraction case. So you get some additional savings by following those routes. We also looked at production of renewable diesel and renewable gasoline rather than biodiesel, partly because these fuels are more easily used in the current fleet than is biodiesel. And you find that the results that you get from these guys are pretty much the same as you would get from biodiesel. Although for these guys, think carefully because there's issues of allocation of the process emissions amongst them because they're co-produced. We've started to think about comparing the results with other biofuels. So here we have the conventional diesel, the algae biodiesel in the baseline scenario that reduced emissions, that first one with catalytic hydrothermal gasification. And then we compared it with soy biodiesel, ethanol from various sources like woody biomass, herbaceous, corn stover, and forest residues. At this point, I guess the point I want to make is that we're starting to make this comparison. We have not thought in detail yet about let me say this differently. I mentioned at the beginning there are issues with regard to how you do allocation when you make comparisons. And at the present time, these studies are using different allocation methods than what I used for this study here. So we need to come back and think about how much of an effect that's producing when you make these comparisons. But in the meantime, as a sort of a flavor for what's going on, it seems at this point that algae offers substantial promise in reduction, but has higher emissions than some of these other fuels that we're looking at and is requiring more fossil energy in its input. So for conclusions, so we see the potential in this model for sort of 50 to 60% relative reductions relative to low sulfur. The fossil energy use appears to be higher than the other biofuels, but there are some cautionary notes. One, this is based upon undemonstrated processes and performances. We've done our best to find things that we have energy numbers for, but as you saw, there are many things that we had to sort of read between the lines. And the second, it's based upon treating the flue gas carbon dioxide as if it were atmospheric. Right? Were it not for that, the results would look different. The key outstanding issues that we identified, electricity and nutrient recovers is essential. But on the other hand, it could be a substantial source of emissions depending upon how you do it. So it's not something that's just for free. We have to think carefully about fugitive emissions. We have to think carefully about the N2O. Let me say this one a little bit differently. We know from Clarence and some of the other analyses that the energy consumption from the nitrogen is substantial. We need to recover as much as possible. To the extent that you don't recover the nitrogen, you're not done with your analysis yet. You need to understand the fate of all the nitrogen in your process as it flows downstream, and that hadn't been included in the other analyses yet. The extraction process in particular, we need something that's demonstrated on wet process. We need improved estimates for a water movement. And I'd like to see that there's some credible evidence that bioflocculation or something for that first level dewatering is going to work. The good news is that these sorts of things that we're identifying, the R&D required for economic viability, the two key factors there were lipid content and productivity. And at least for those variables, the GHG requirements and the economic requirements are working in the same direction. They're not at odds with each other, and that's an encouraging thing. But do be careful. It could be that for control of fugitive methanes and emission and nitrous oxide emissions, maybe they go in opposite directions depending upon what you do. So there is a place to sort of keep an eye on things. But at the moment, it appears at least they seem to go in the same direction, be driven in the same way. Future work in the coming year will be to work on harmonization with techno-economic and resource assessment models so we can get a broader idea of how these various variables interplay. We want to increase our community engagement so we can get better process data, expand the process inventory, and help people do additional analyses so we can compare more algae scenarios, and add new pathways. Hydrothermal liquefaction, heterotrophic growth in particular, are high on our list for ones to include. We want to finish the photobioreactor model, and we're going to make sure, double check the infrastructure materials. I don't think it's a large effect, but we need to calculate it out. So I'd like to thank our funding, our agency for supporting us through the Office of Energy Efficiency and Renewable Energy, in particular Joyce Yang and Zia Hawk, who have supported us, our program managers. I guess this has changed. That report is available now. And I'd be glad to take questions. Thanks for your attention.
Questions?
Probably numbed you with all the details.
In a practical application of this, would it be like at a power plant and you would extract the methane and that would supplement the natural gas from the boilers, and then the lipids could be converted to a biofuel which their vehicles could use?
There are various approaches that people are considering for how you integrate the pieces together. The scenario that you described seems similar to the one that Stevenson considered, in which rather than producing electricity on site, they upgraded the gas to sufficient quality to return to a nearby power plant, which then used it in engine boilers for the electricity production. In the scenario that we considered here, we combust the biogas on site after only enough cleanup to make it amenable for combustion in a turbine, and then take the electricity and use it on the site. Part of the motivation for that is, at least within the U.S., there's much more opportunity for making use of coal power plants than there is today. That's one reason for it. But this picture of how you put the pieces together, there are many things that people are considering. And the one you described is one. The one we described here is a little bit different. The integration is just by having the CFP on site. And that partly also gives you access to some of the processing, for example, for the next analysis.
My question was similar. Can you use the capture CO2 if it is side by side with ethanol production, let's say for ethanol plant or any other ethanol plant? The CO2 is there.
Exactly. And in fact, there you have an advantage that in those processes, the CO2 is being produced metabolically. It's a pure CO2 stream. So I didn't get into this detail earlier. I mentioned that if you try to transport pressurized CO2, you suffer a penalty for pressurizing. So since we're transporting flue gas, which is only about 10% by weight CO2, we're spending a lot of energy moving gas that is not useful to you. So if you're working from the source, let's say from ethanol, which is a pure CO2 stream, you have much higher capability to transport that downstream. If you look at the flue gas, it looks to me like maybe you go a few miles before you really can't afford to go much further. That comes from two things. So it's partly from Veneman's estimate that estimated that the economic cost of building a pipeline, by the time you get to a couple of miles, no longer pays for itself. But the other factor is, by the time you start getting that far out, the area of the farm being supplied is requiring a larger pipe than what you could really build. Or maybe a better way to say that, the volume you have to put through. So yes, that is an opportunity, and it's a nice one if you look at from let's say ammonia production or from ethanol production where you have a pure CO2 stream. That's nice. But the challenge in all of these is will there be land nearby that you can actually use for growing
Is
I'm really interested in this question of fugitive emissions. I mean, so and how it seems like there's a lot of this is very sensitive to, I mean, especially considering things like N2O having much higher greenhouse gas effect. And the whole idea of cultivating algae is going to be this acceleration of nitrogen, large amounts of nitrogen being used. The small uncertainties in like N2O emission factors, fugitive emission factors. And right now you're only considering in the anaerobic digestive process, right? Or and then the field application, but I mean there could be fugitive emissions and other steps and things ultimately. Like for the extraction, we consider things like potential hexane fugitive emissions that they're not going to. Some of this might get released.
So in that regard, the N2O that we're considering right now is the emissions from application of the digestate enzymes. You could also wonder about emissions of N2O from the culture. In that case, I'm aware of one study that was done in Colorado or Kansas. They were looking at small flasks. And there they discovered that if they produce an anaerobic environment in the headspace, corresponding to what you might have in a photobioreactor in the evening, then they see N2O production. And they did some assays on the culture and also demonstrated the presence of, I think it was more so the appropriate gene from an associated microbial population in the culture for production of the N2O. In the case where in the evening you maintain an oxygen environment above the culture, in that case they didn't see. Now, the thing I would say, though, is that we're only looking at a few centimeters thick, whereas the culture is more like 20, 30 centimeters. There was a poster at a conference last week in which Solana had done some measurements looking at a raceway pond. And there they did observe N2O being emitted from this open pond, suggesting that there must be anaerobic portions within, whether that's algae that settles at the bottom or just from the nature of mixing situation. I fooled around with their numbers a little bit, and it looks like it would be a fraction of what we're seeing coming from the field. The good news in this regard is the cost of fertilizer is an important economic driver. So in making the economics work, the producers, the process developers, are trying to get the highest nitrogen recovery they possibly can. I think Sapphire is the one that says that their goal. Their goal is complete nitrogen recovery. The only thing they want to see coming out the door is a fuel with no nitrogen and no phosphorus. Whether they achieve it, I'm not so sure. But understanding the fate of nitrogen process, fortunately, economic drivers will push us.
I came in late, you might have covered this, but you mentioned anything about water use and degradation?
We did. We focused on emissions, air emissions, and did not focus on water consumption. We followed water only to the extent that it would introduce a substantial energy demand for its transport. But beyond that, we didn't try to account for the environmental impact of water consumption, eutrophication, and so forth. There's a study that's been done by PNNL recently that's looked at water consumption, and they've gone into this in tremendous detail based upon models of growth and GIS data, so it was site dependent, and then have currently moved on to looking at water resources. So we didn't consider that portion in our analysis deliberately, except as it affects the energy consumption. But it's a very important thing to consider.
And it is a significant amount of water.
In their modeling, it's turning out to be a substantial amount. It's interesting when you hear discussions of it, you'll hear some people say, well, if you look at can evaporation from the surface of the pond, you'd actually expect that to be substantially less than evapotranspiration from an energy problem. Other people will then compare photobioreactors to the pond and say, well, you're going to have so much more water loss from the pond, and others will say, well, not when you actually consider spray pool for your PBR. But I haven't seen good numbers for any of these. So I think it's an important question. I think there are a lot of question marks.
I wonder if you could put up your pie chart of the emission movement.
It's like slide 95 or something, right?
So in here, the oil conversion to fuel is just transesterification of the oil.
This is transesterification, that's right. So that's a mixture of process heat, consumption of some methanol, methanol recovery.
Okay, so that's the biggest component. The second one is nutrients. If the nutrients were supplied from wastewater, could that go to zero?
There is an assessment of that in a study by Lundquist et al., 2010. Let me give two different answers. The answer is yes, but you will be limiting your ability to scale up according to the availability of wastewater and land nearby the wastewater treatment. And for that reason, in our study, we didn't consider wastewater as a source of nutrients so that we could complement that analysis that had been done already and try to see how much further we might go. Similarly, our choice of a wet process was to complement their approach of using solar drying and then going into a regional dry extraction process. So you could, but we deliberately chose not to. And if you do, you have to think about the resource potential.
So you're just looking for makeup nutrients because you assumed a significant nutrient recycle through
That's
anaerobic digestion.
And these are makeup, so it's already been subtracted for the amount that we've.
So I would submit if it's just makeup nutrients, it actually scales quite well.
Mm-hmm.
You could still make a lot of oil based on the available wastewater nutrients.
I would agree, depending upon how far you succeed in your nutrient recovery. That's a key question. But the other thing you'll have to feed into that, though, is regardless of your ability to recover, you still have to consider the number of waste treatment plants, the location, and land nearby to grow in. But I would agree for regard to the NMP. It depends on how you do it.
And the other thing is you mentioned using liquefaction as a replacement for anaerobic digestion in your model.
As a replacement for the entire conversion step.
For the entire conversion step.
Yes.
Okay, so it would potentially address the 24% here that's
Yes,
goes to transesterification.
It would affect, I think, a number of things. It would affect this step. It would affect the way that you do dewatering.
Yeah.
It would remove this step. I have to think hard about that one.
And you will based on that still 25% of the content
For which one?
for this analysis.
This is all based on the 25%.
25% and 25 grams per square meter production.
Correct. So we chose those. Those parameters are largely a matter of choice. You see such a broad range, and it's going to depend upon the species, it's going to depend upon where you're growing. So we chose what seemed to be sort of a conservative value, and then use a sensitivity analysis to see how much it would change. One thing that seems to be emerging in the discussions I've heard is that there's a sense that it will be easier to increase the lipid fraction than to increase the productivity. And that was the motivation in the reduced emission scenario in A, that I increased the lipid fraction but didn't change the productivity. So that's how we explored that space.
So, go ahead.
Am I correct in assuming that the raceway ponds are limited to climates south of here?
I would say so. People are exploring other algae that can be used. Of course, by the time you get to the point that the water freezes, you're done. I think warmer climates are explored.
Lance?
I was just going to say on the wastewater one, if the wastewater plant was actually forced to remove nitrogen, they would spend energy and have greenhouse gas emissions associated with that. In that situation, would you consider a negative and essentially a credit for the nutrients if you use wastewater nutrients?
I think that would be fair. I think the key question is you're comparing A with B, and you want to make sure that the two scenarios are consistent. So if the thought in the scenario is that by introducing this we obtain a way to, let's say, effectively reduce our production of ammonia, that would be a fair displacement credit. These are the sorts of things that LCA analysts just argue a great deal. And it makes a good point because it points out the importance to consider the economic consequences. You shift the markets around you, and you have to consider that effect.
As a result of the second dewatering, we got the solid concentration about 200 grams per liter. How is that number decided?
So that number comes from basically performance of centrifuge. So you get sort of 8 to 10% out of dissolved air flotation, and that determined the volume that was then brought into I think we used a disk stack centrifuge, using energy consumption there. So the strategy there was to just keep getting rid of as much water as we could with the less energy intense processes. But then to get to that drier level required that centrifuge.
Basically, it's kind of optimization.
Not that we've done the optimization.
One last question. How about the land requirements? Yes, you're not going to be using agricultural land, but city land to produce ponds or whatever technology is. Where are the lands and how much land is available? How much can be produced by that?
So there would be two parts to the answer to the question. One is on the life cycle analysis side, the importance of the land would be to include land use change in the algae life cycle analysis, as is done, for example, with corn ethanol. And in that case, we've not included it yet, partly with the intuition that the productivities for algae per acre are so much higher than the other biofuels that we think that it will be a very small effect. We'll come back and revisit it later. The second half of the question is more along the lines of resource assessment to determine potential for producing algal fuels. And the feedback there to life cycle analysis is the location of the land is going to determine the species that you can produce, your productivity, and so that would affect the life cycle analysis. We have not done a site-level life cycle analysis yet. I mentioned the harmonization work, and one of the things I hope we might be able to do is to start making use of the work done by Pacific Northwest National Lab and some of the other people that are doing the resource assessment in order to do those sorts of studies. But if you're interested in that question, take a look at the report from PNNL. I forget the lead author's name, but certainly Wood Mosta was one of the authors on there. And they've gone through using GIS data to identify places with suitable slopes, suitable weather conditions. They've identified the pan evaporation and so forth and so on, and use that to assess potential for algae. And in that same report to assess water consumption.
Thank you very much.
You're welcome. Thanks for having me.